Welcome back. Today we're going to talk about section 4.3, which is on graphing functions, and we're going to start with number 9, which asks us to sketch a graph of the function f of x equals x cubed minus 6x squared plus 9x. All right, so the goal here is to sketch a graph of this function, and we're going to use the first derivative and the second derivative to help us to do that. And the way that that's going to work is the first derivative tells us some information. Typically, the first derivative gives us a little bit of information about where the function is increasing, decreasing, and where the local max and mins are of that function. And then the second derivative gives us information on the concavity of that curve. And if you want to use the second derivative test on the maxes and mins, and also on any inflection points. So what we need to do is we need to look at this function, take its first derivative, get all the information that we can from the first derivative, take a second derivative, get all the information we can from the second derivative, and then use all that information together to sketch the curve. So let's do it. So first thing I want to do is let's just take the first derivative of this function, and that's easy enough to do. So we take the first derivative and we see that it is 3x squared minus 12x plus 9. And maybe we want to even factor out a 3 from this thing. So we could say that f prime of x is equal to 3 times x squared minus 4x plus 3. And the reason that I do this factoring is I'm wanting to find the critical points of the first derivative. And so I could factor this. And if I do, I get f prime of x is equal to 3 times, let's see, I guess this would be x minus 1 times x minus 3. All right, so this gives us some critical points for this function. And the critical points are going to be x is equal to 1 and x is equal to 3. So here are my critical points. So first thing I want to do over here is let's just draw a number line. Here I'm going to put f prime to remind me that this is information about the first derivative. And I know that my critical points are 1, so I'll put 1 on there, and 3, so I'll put 3 on there. Now I want to test points in between to get all the information I can out of my first derivative. So I want to test something here, test something in this interval, test something in this interval to see if I get positives or negatives on the various intervals, which will tell me if my function is increasing or decreasing on those intervals. So let's test something over here. Maybe 0 would work. And remember, I'm testing that in the first derivative. So if I put a 0 into the first derivative, let's just look right here. I'd get 3 times a negative 1 times a negative 3. So a 3 times a negative is positive, and I'd get positives here. Remember, all I care about is if it's positive or negative. I don't necessarily need to get the exact answer. I certainly could. It's 3 times negative 1 times negative 3, which is 9. But all I really care about is if it's positive or negative. If I take something in here like 2, I'll do the exact same thing. I'm going to plug 2 into this first derivative right here. But I don't really care what the number is. I just care if it's positive or if it's negative. So 3 times 2 minus 1, well, that's 1, which is positive. And 2 minus 3 is negative. So it's 3 times a positive times a negative, which is negative. So I'll fill this in with negatives. And then I want to test something over in this interval. How about a 4? So if I plug in a 4, I get 3 times 4 minus 1 is positive, and 4 minus 3 is positive. So positive times positive is certainly positive. Okay, and now I just remind myself, okay, what does this tell me? If I have positives from negative infinity to 1, that means that this thing is increasing or going up. Negatives mean it's decreasing or going down. And positives tell me that it's increasing we're going up. Also, I can see I get a local maximum at 1, and I get a local minimum at 3. All of that information I can read straight off of that first derivative chart. So now I want to do a similar chart for the second derivative. So I want to go back over here. I have my first derivative. I already got my critical points and everything on my chart. So let's erase over here a little bit. And now let's look at the second derivative. So I get f double prime of x is equal to 6x minus 12. Of course, I could factor out a 6, right? So f double prime of x is equal to 6 times x minus 2. And so the only critical second order critical value, or critical value of the second derivative that I get, so second order critical point would be at x is equal to 2. That's the only thing that would make the second derivative 0. So I get this second order critical point of 2. So let's come back over here again. We'll make another number line. Call this one f double prime. And the only thing of interest is 2. So now I want to test the intervals on both sides in the second derivative to see would it be positive or would it be negative. So if I test something over here, like let's say 0, in the second derivative, I plug in a 0 and I get 6 times negative 2, which is certainly negative. So I can fill in over here with negatives. And if I plug in something over on this side in this interval, like maybe 3, I plug in 3 and I get 3 minus 2 is 1 times 6 is 6, which is positive. So I put in some positives. And now I remember, okay, in the second derivative, negatives mean concave down, and positives mean concave up. And this point in between where it switches from concave down to concave up, we call a point of inflection, or an inflection point. So here would be an inflection point. So now let's put it all together and see if we can sketch a graph here. Before I do, let's take these points. You see, 1 is kind of an important point, x value in this problem. 2 is an important x value, and 3 is an important x value. So let's take those 3 important x values, and I just want to come over here real quick and say, well, what would f of 1 be? What is f of 2? What is f of 3? It just makes my graph a little cleaner if I have some sort of anchor points to start at. So these are important points to this function. So let's just see what their functional value is. So if I plug in 1, I'm just going to do it real quick here. I get 1 minus 6 plus 9. So that would be, what, 4? So I get a 4. So f of 1, draw my axis extremely well here. I want 1 to be here. I want 2 to be here. And I want 3 to be here. So 0 would be back here. This is much better. Okay, so f of 1 is 4. What would f of 2 be? Let's see. So f of 2, plug it into the original function, I would get 8 minus 6 times 4 plus 9 times 2, right? So this is minus 24 plus 18 is minus 6. It would be 2. Okay, so 8 minus 24 is negative 16 plus 18 is 2. Right. Okay, and what about f of 3? So let's figure that out real quick. So f of 2 is 2. And finally, f of 3, let's figure that out real quick. I get 3 cubed, which is 27, minus 6 times 2 squared, 3 squared, which is 9. And then I get 9 times 3 plus 27. Okay, 6 times 9 is 54. 27 plus 27 is 54. So I get 54 minus 54, or 0. So this is 0. So f of 3 is 0. Okay, so now that I have these 3 points put onto my graph, I think I'm ready to draw this thing. And the way that I want to draw it is I want to start on the left-hand side of these number lines and work my way across. So starting on the left-hand side and coming in this way until I get to the first important point, which is 1, what I see is I'm going up. I start out going up, and I'm concave down. So I'm going up, and I'm concave down, so something like this. I'm going up, but the concavity is down. Then it changes at 1. At 1, I start going down here, and I'm still concave down. So instead of going up, I'm going down, but I'm still concave down. At 2, things change again. I'm still going down, but now I'm concave up. So I'm going down and I'm concave up. And then finally, from 3 to infinity, I'm still concave up, and now I'm going up. So we were able to sketch a graph of this curve, and it would look something like this.